Okay, so in this video we're going to talk about comparison tests. Now, the first thing that we want to do is, in the comparison test, the idea is basically to compare a given series with a series that's known to be either convergent or divergent. We can use any series that we can show as convergent to use it as a comparison, but we often either use p-series because a p-series converges as long as our p is greater than 1, and diverges when p is less than or equal to 1, or a geometric series, because we know that a geometric series will converge as long as our common ratio is less than 1, the absolute value of our common ratio, and diverges any other time. So other than using p-series or geometric series, we get creative otherwise, but in general, kind of our go-to standards are going to be p-series and geometric series. Those are like old reliables. All right, so we're first going to talk about what we call the direct comparison test. So suppose that we have some sequence a sub n and some other one b sub n, and then we take their series. Okay, their series and their positive terms. If our sum b sub n is convergent and a sub n is less than or equal to b sub n for all n, then a sub n is also convergent. And in the same concept, if b sub n is divergent and a sub n is greater than or equal to b sub n for all n, then a sub n will also diverge. So let's talk about that visually, because I know that that notation can maybe be a little bit overwhelming. Now, if we have some, let's call it a function for the time being, and it's this, okay? So this is our like a sub n. And we have some b sub n here. Now, if we can show that this converges, then it would make sense that a sub n would also converge, because a sub n is less than b sub n everywhere. And if b sub n converges, then adding up all of a sub n should also converge. And in the same regard, if we switch this and we were to say, okay, well, let's say that on our next one, this is now b sub n here, b sub n. And we know that b sub n here diverges. Then, obviously, if this diverges, this also must diverge. Okay, because a sub n in this case is greater than or equal to b sub n for all that. So basically what we want to do is we want to go, all right, we'll come up with some series that we know converges or diverges depending on the situation, and use it as a comparison. Now, obviously, if b sub n converged, then we don't really know if a sub n will converge here, because a sub n is above it and it could converge, it might not. So, for example, we know that 1 over x, this thing here, this is a p-series equal to 1, and it's actually the harmonic series. We know that this does not converge, but 1 over x squared does converge. Okay? Now, if we know that this converges, we don't know anything about this one converging or diverging because it's not less than it. And in the same thing here, this diverges and this one's less than it, but that doesn't necessarily tell us anything, because we know this diverges and it's greater than it. We don't really know about what anything less than it. It'd have to be greater than. So in that case, like if we change this to 1/2, okay, something like this. Now, we know that this black one, the harmonic series, will diverge. And since this one's greater than it, it would also diverge. So that would make sense to us. Okay, so that's kind of the idea here. So we just want to come up with something else. All right, so let's take a look at how we use this. So determine whether this series converges or diverges. Now, in general, what we want to do is we want to try and rewrite these things in terms of some kind of p-series or geometric series. So here, I mean, if we look at that portion, that's basically a p-series. So we want to try and compare this to the p-series n to the third. Okay. Now, this thing here is clearly less than or equal to this one. In fact, it's strictly less than, but we'll stick with a less than or equal to. So this one, no matter what n is, it will always be less than this one, right? So we're here, and we know that this converges. And since it converges and this thing here is less than it, then this also converges by direct comparison. By direct comparison. It's nice to know how we know it converges. Now, if we take a look at their graphs here, we have 1 over x cubed, and we have 1 over x cubed plus 8, okay? So we can see here that for all the purposes of, for us really, we're looking from 1 onwards, and that's sufficient to show from 1 onwards for us. We can see that our green function is in fact less than or equal to our blue function. It's always a bit below it. So if the blue one converges, then obviously the green one must. Okay, let's take a look at another one. All right, so we have this thing here. Now this is maybe not as obvious of what kind of series this thing might look like, but let's kind of rewrite this a little bit and also drop constants as much as possible. So here we have n plus 1 over n square root n. We're also going to write the other one, so I'm going to drop that 1 off, and I'm going to rewrite this thing here as n to the, this is a 1, this is a 1/2, so we add them, so that would be 1 1/2, which would be 3/2. Okay? Now, I'm going to simplify this a little bit, this thing here. This is n to the 1, so this would be 1 over n to the 1/2, something like that. Okay, so basically what I did was I just dropped the constant here. So now we're going to use this to compare and see if it gives us the statement we want. Now, there are times where you find something, you go, oh, this will be a great comparison, but it doesn't reach the things that you want. Well, that's not really a deal breaker for us. I'm going to actually leave that. I was going to delete the other one, but I've decided to keep it. So I'm just going to rewrite it and not be lazy. So if we have 1 over n to the 1/2, now we dropped a 1. That's all we've done to this. We got rid of this 1. So our top here is smaller than it used to be. The bottom is still the same value. So functionally, after we've canceled things. So we know then that this thing here is greater than or equal to this one. Okay, because again, the top is just n instead of like n plus 1. So we just dropped it. Again, we're using this but simplified to that. So we know then that this right here, this is a p series where our p is less than 1. So this is going to diverge. Okay, so if this diverges and it's less than this one, then this must also diverge by direct comparison. Okay, so let's take a look at this one. Determine whether the series converges or diverges. We have 1 plus cosine n over e to the n. Now, if we think about this, 1 plus cosine n over e to the n. And we want to think, what can we compare this to? Now, the natural inclination from the previous ones is to drop this 1. But instead of dropping that 1, let's just think about what is this cosine n actually doing for us? Well, cosine n, we know, goes between 1 and -1. So on top, the numbers will go between -1 here to 1. So that means 1 minus 1 is 0, or 1 plus 1 is 2. So basically, it's going between 0 and 2 on top over e to the n. So all I have to do then is go, all right, well, I'm going to compare this 1 plus cosine n over e to the n with 2 over e to the n. We know that at most this can be 2, but in general it's somewhere less than that. So we're using this as a comparison. Now, if we think about this thing here, this is like saying this one right here. This is a geometric. Okay, we recognize the geometric, and I recognize I'm going to be using a geometric because this is e to the n. That's exponential. Any constant to some variable is an exponential equation, and geometrics describe exponential equations. So, or exponential functions. So we're using this thing, and we recognize this as a geometric. Now, this would be like 2 times 1 over e to the n, something like that. which is like saying 2 times 1 over e to the n. So this 1 over e is our common ratio. And we know that 1 over e, absolute value, is less than 1. And since it's less than 1, this thing here converges. And since it converges, then this also must converge by direct comparison. All right. Now, let's talk about estimating these sums. Now, if we have used direct comparison test or whatever to show that a series converges by comparison with some other series, b sub n, then we may be able to estimate the sum by comparing the remainders as well. So as a reminder, the remainder of some value is our error, right? And it's equal to our infinite sum minus our partial sum. So essentially, if we do the 10th partial sum, it would be the 11th, 12th, 3rd, 13th, 14th, etc. onto infinity. It'd be what's left. And since we know that the comparison series also could have some remainder here, t sub n, we're just going to call it t, so it's not s sub n, it's t, the next one, okay, is the infinite series here minus the partial sum. If we define these that way, then since a sub n is less than or equal to b sub n for all n, then we know that our remainder, r sub n, for a sub n, our remainder for a sub n, is going to be less than or equal to our remainder for t sub n. So we can just use t sub n to find our estimation. And we can also kind of find exact values with a geometric if it's geometric, but with p-series we can just do our, for both we can really just do our improper integration to find that remainder. But essentially, the reason why we're not just, the reason in the first place we're actually doing this direct comparison is because the integral test is something we can't necessarily do for these because we don't know how to integrate this or this one or that. Like this, we don't really know anything to do with integration of it. So, or maybe it's not so simple. If we see a basic integration, cool, we could just do that. But essentially the issue is we don't really want to integrate it. So if we have to integrate our remainder anyway, do an improper integral of it, then that kind of sucks. So instead we just go into a simpler function like a p-series or geometric series and integrate that, and that would be a lot easier for us, and then that would set our maximum error rate. So let me show you what that means. So we're going to use the sum of the first 10 terms to approximate this sum of this series and estimate the error. Now, first of all, that's assuming it is convergent. So let's just double check that it does in fact converge. So I'm going to do 1 over 5 plus n to the 5th, and I'm going to compare it to 1 over n to the 5th. That's a p-series here, and we know that it's definitely going to be greater than or equal to this because this bottom here is bigger than this one, so this is a bigger number. This converges, so this must converge. Again, this converges because it's a p-series and its power here is greater than 1. Okay, so we know it converges. All right, so now what we're going to do is we're going to use our 10th partial sum. So that would be the sum of the first 10 terms. It's the 10th partial sum. So here we're going to take from n equals 1 to 10 of our thing. We're not going to use this like our comparison one because the comparison is not going to be a good sum estimate to this. This is going to be the best estimate to the infinite sum is to use the actual sum we're talking about, the actual sequence we're talking about. So we're going to do 5 plus n to the 5th. So we're taking the first 10 and we're adding them up. And we're going to get some value. So let's go to Desmos and find what that value is. So if we go down to calculus here. Okay, so n equals 1 to 10. We are going to get 1 over 5 plus n to the 5th. All right, so we get that this is equal to 0.19926270345.9. Okay, so this is our approximation, and again, it's an approximation to our infinite sum. We're just adding the first 10. obviously that's an approximation. It's not going to be perfect. So now let's compute, what's our error? So our error is the remainder of them, essentially the integral from 10 to infinity of this 1 over 5 plus n to the fifth. However, this is problematic because integrating this is challenging. That's the whole reason we just wanted to do direct comparison anyway. So we know, though, that this must be less than or equal to the integral from 10 to infinity of 1 over n to the fifth, because again, this is always bigger than this anyway. So if we're adding up each one of those smaller terms than this, then it would add up to be less than this, clearly. So we're using this as our estimator then. Essentially, we're going to say that r sub n is less than or equal to our t sub n, which is equal to, well, which is, nope, should not have gone back that far. Less than or equal to our integral from 10 to infinity. And technically speaking, it's actually equal to it. Okay. Well, I guess we would do a less than or equal to as well here. Anyway, so of 1 over n to the fifth. So we're going to integrate this thing. So that means we're going to take the integral of n to the negative 5 here, negative 5. So we're integrating this. So the integral of n to the negative 5, that's going to be n to the negative 4 over negative 4. So that is to say we're going to take the limit as n approaches infinity. I guess actually we'll do limit as t approaches infinity. I'll do a different thing from 10 to t here. I mean, we can use any variable, but just so that I'm not replacing everything with the same variables. Okay, so if we take a look at this, t comes into here as negative 1 over 4 t to the fourth minus negative 1 over 4 times 10 to the fourth. So this is the limit as t approaches infinity. So at infinity, this right here goes to 0. So we have 0 plus 1 over 4 times 10 to the fourth, which is going to be some value. 1 over 4 times 10 to the fourth is 0.02, there's 4 zeros, 0.00025. 0.00025. Okay, cool. So this right here is our error rate. So again, our remainder at sub 10 is less than or equal to this 0.00025. So this estimate right here, our 10th partial sum, is pretty darn good. I mean, we're approximating out tens, hundreds, thousands, 10,000s, 100,000s. I mean, 200,000s. That's pretty accurate. Okay. So again, we want to check, first of all, that it converges, but then we can find an approximation and then check the error. And if we don't like that error, like if we feel like that's not good enough, we can always take a larger partial sum. So maybe the 100th partial sum or something. Anyway, let's take a look at another one. Okay, use the sum of the first 10 terms to approximate the sum of the series and estimate the error again. Now, that's again assuming it converges. Again, if it diverges, we can't find an infinite sum. It goes to infinity. So that's the whole point, is we have to make sure it's convergent before we bother wasting time with that. So let's go ahead and take a look at that. We have 5 to the negative n. Now that screams exponential to me. I mean, because that's an exponential right there, this portion. And since it's exponential, I'm definitely thinking geometric. Okay, so we have this thing. Now let's think about cosine squared. So again, same concept as before. We know that cosine goes between 0 and, or excuse me, -1 and 1. And so cosine squared here must go between 1 and 0. So essentially, this will either be 0 or 1. So in general, it's some kind of fraction, but at most it's just 1 times this. So 1 times this would just be itself, and anything less than 1 would just be a fraction, so it would be smaller than this. So we know then that this cosine, this thing here, the series that we're dealing with, must be less than or equal to 5 to the negative n. Because again, this 5 to the negative n here, or I should say this cosine squared, is generally going to make this smaller than 5 to the negative n, or at the very most, it will make it equal to it. So we're just going to compare these. Now, this right here is, again, a geometric series. This is 5 negative n cosine squared n is less than or equal to, this would be like 1 over 5 to the n, which we could just write it as, if we pull that n out like that and do a parentheses, because 1 to any power is just 1. So we're going to write this as 1 over 5 to the n, and we see that this right here, 1 over 5, is the ratio, and it's less than 1, so this converges. And since it converges, and this is less than or equal to it, it also converges by direct comparison. So this is what we're going to use as our comparison function. All right, so we know it converges. Let's find the 10th partial sum. So n equals 1 to 10 of 5 to the negative n cosine squared n. And we will get that. So let's go to Desmos again. I'm just going to use this again. This will be 5 to the negative n cosine squared n. All right. So we get this value here. That is 0.07392930333785. So that's our 10th partial sum. Now we want to know, okay, well, how good of an approximation is that? So again, same concept as before. Our remainder of 10 here, so anything past that, that's going to be less than or equal to our integral from 10 to infinity, which is of this 5 to the negative n cosine squared n, which is obviously less than or equal to the integral from 10 to infinity of our 5 to the negative n. So we're going to go ahead and use this one instead, because we can integrate this a lot easier. Now this is an exponential. Now as a reminder, sometimes just normal exponentials kind of give me a little bit of issue. So I think about e to the x. The integral of e to the x is e to the x. Now why is that? Well, it's because it's e to the x over natural log of the base e. That's actually the integral here, and so that's what's going on here, is the integral of this would be 5 to negative n, okay, leave it alone, divide by this natural log of the base, 5, and then we have this negative as well, because this is a negative and not just a positive one, so kind of a negative 1 if we have that, or really divided by negative 1 technically speaking, but it's times, doesn't matter. We can find that through u sub, so basically if u was negative n, then du is negative 1 dn, something like that. So that's where that negative comes from. Okay, so we integrated that. So that is to say our remainder is less than or equal to this thing, 5 to the negative n over ln 5, and it's a negative of it from t to, or from 10 to t, and it's the limit as t approaches infinity. Okay, so let's take a look at that. This thing here, this would be negative 1 over natural log of 5 times, this 5 here is on the bottom, 5 to the t, minus negative 1 over natural log of 5 times 5 to the 10th. Okay, now if we take the limit as t approaches infinity, at infinity, 5 to the infinity is infinity, times the constant, still infinity, 1 over infinity, that's a 0, plus 1 over natural log of 5 times 5 to the 10th. Okay, so we need to find what that value is. I mean, we could leave that technically speaking, but we usually write it as a decimal, so let's go ahead and find what that is. Times 5 to the 10th. Okay, so this right here, our remainder, is quite small. r sub 10 is less than or equal to this 6.36246972299 times 10 to the negative 8. So really, 1, I should shift this. Ooh. All right. Basically, 1, 2, 3, 4, 5, 6, 7, 8. So 1, we would need 1, 2, 3, 4, 5, 6, 7 zeros in front of it. Tens, hundreds, thousands, 10,000s, 100,000s, millions, 10 million, 100 millions. So it is very accurate. This is a really good approximation to our sum. All right. So that is, again, how we can approximate our sum and determine our error. We approximate our sum the exact same way as we've done before, but we approximate our error using this nicer to integrate comparison function. Okay. So let's now talk about the limit comparison test. Now, direct comparison is only conclusive if the terms of the series being tested are smaller than those of a convergent series or larger than those of a divergent one. But what about this series right here, 1 over 2 to the n minus 1? Now, we can't use direct comparison because if we do 1 over 2 to the n, that would be a geometric that converges, but 1 over 2 to the n minus 1 makes this function bigger than our convergent series. But they're really close, so it should make sense that the two should still converge, because really, do you think this minus 1 should really be making that big of a difference to this? When you compare, I mean, especially if you compare, like as n gets bigger and bigger, I mean, minus 1 is meaningless. So we'd love to use direct comparison, but we can't because this is greater than this one, and this converges, so that tells us nothing about this. So what we do is we go to the limit comparison test. So suppose that a sub n and b sub n are series with positive terms. If the limit as n approaches infinity of a sub n over b sub n is equal to some constant, where this constant is a finite number and it's greater than 0, then either both series converge or diverge. So if we know that one converges, then they both converge if they meet this requirement. Okay, so let's take a look at this one again real quick. So again, we know that, let's see this in action. Ooh, that's a little big. Okay, so we know that we can't do direct comparison because this 1 over 2 to the n is greater than this one. So that's not going to work. But we do know at least that this converges. And we know it converges because this is a geometric series. It's 1 over 2 to the n. This is a geometric series with r less than 1, so it converges. Okay. So we know that this converges, so what we're going to do is we're going to use it, and essentially we're still using, as a comparison, we're still using the same things that we'd probably use in direct comparison when we're doing this limit comparison test. So again, I'm not choosing something at random, I'm choosing basically the same two functions. Okay, so what we're going to do is we're going to show that if we have, again, oh, I have it here. If we have these two series, if I take this one that I'm dealing with and I divide it by this one, the second one, the one that we want to compare it to, then if we can get some number as n goes to infinity that's not infinite and not 0, then we can show that they'll both converge. So that's what we're going to do. We're going to take the limit as n approaches infinity of 1 over 2 to the n minus 1 divided by 1 over 2 to the n. And we're going to see what this goes to. Now, this is kind of our fallback if other things don't work out. We'd like to not have to do this, but you know, if we can, we'll take a look at it. So this is like saying the limit as n approaches infinity of 2 to the n over 2 to the n minus 1. Now, we know from pre-calc horizontal asymptotes, right? So when we have these things at the infinites, what are the two terms that actually matter? Well, they're the leading, the most powerful kind of portion of it, the most powerful term. So in this case, it's the exponentials, because at the infinites, minus 1 is meaningless compared to 2 to the infinite. Okay, so basically this is equal to 2 to the n over 2 to the n, which is 1. And so now it's the limit as n approaches infinity of 1, which is just 1. So by the limit comparison test, these two things converge. Because again, this one converges, so this also must converge. Now, this is the way I like to think about these, but if you may have been taught it differently. I know I don't really like it that much, so I mention it in my classes, but I don't really do it too much. But basically the idea is when you have this, it's the same concept of what we just did where I'm looking at the most powerful one, but basically what you do is you take the highest power, the most powerful function in the entire thing and divide every term by it. So that is, you take this 2 to the n and you divide it by 2 to the n. And you take this 2 to the n, and so you're dividing it by 2 to the n. And you have this minus 1 over 2 to the n, because we're also doing that one by 2 to the n. So this would end up being like a 1 over 1 minus 1 over 2 to the n, and we take the limit as n approaches infinity. So this stays at 1, this stays at 1, and this is 1 over infinity, or 0. So that is to say it's 1 over 1 minus 0, which is also 1. So depending on how you want to think about it, it's all the same, but basically we showed that this is in fact 1. You could also technically use Hopital's rules, I suppose, as long as they are indeterminate, infinity over infinity or 0 over 0, you can use Hopital as well, but that's overkill, I would say. So, and also the derivative of that, well, I guess that would simplify. It'd be 2 to the n over 2 to the n, and that just becomes 1. Okay, so anyway, the point is that we showed it converged. Let's take a look at another one. So determine whether the series converges or diverges. Okay, so first of all, looking at these two things, we have, I guess we can distribute these things. Now, I'm thinking I'll probably end up like dropping something like this. Okay, that's probably one of my goals. I mean, I might also have to drop this one, this minus 1 potentially, to just make my life a little bit better. So let's take a look at it. We have n plus 1 over 3 to the n cubed 4n minus 1. Okay, now if we take a look at that in comparison to n over 3n cubed times 4n, which would mean that we are comparing it to, rather than this, that would be n over 12n to the 4th. Okay, now we don't really know how these two things compare, but this might be beneficial. This might be something I do. Because the problem is we're changing the top and the bottom, so we don't really know if it's like greater than or less than necessarily. So rather than doing that, we can also consider maybe I should just start in like one position. Maybe I should just take a look at we'll stick with this one, but we might have to go to using like n over 12, well, not 12, n over 3n cubed 4n minus 1, something like this, where we just drop the 1. Maybe that would be good enough, in which case we know then that this one's greater than this one. We might use that, because dropping it entirely might be a little much, but I still don't really know how to integrate this, and I don't know if this one converges or not. So that's why I'm probably not going to go with that. Let's take a look at this one. This is 1 over 12 n to the 3rd. Now, this thing right here is a power series. It's 1/12 times 1 over n cubed. And since this thing here converges, because it's a power series and this power here is greater than 3, or greater than 1, it's 3. So we know that this at least converges, so maybe we can use it as an approximation to the other one. So we're going to take our n plus 1 over 3n cubed 4n minus 1 and see what we can do with it. We're going to divide this by 1/12 n cubed, like that. Okay, and we're going to take the limit as n approaches infinity of this quantity and see what we get. You know, we might get something nice. All right, so we end up with n plus 1 over 3n cubed times 4n minus 1 times 12n cubed over 1. Okay, n cubes will drop, and we have 12 and 3. This becomes 1, this becomes 4. So we end up with n plus 1 times 4 over 4n minus 1 as limit as n approaches infinity. Okay, so that means we have 4n plus 4 over 4n minus 1. And we're going to do the same logic we did before, either by dividing everything by n, which is the highest power here, or just thinking at the infinites, only 4n matters on top and only 4n matters on the bottom. So that means it's 4n over 4n, which is also 1. And so because this is greater than 0 and not infinite, they both will do the same thing, in this case, converge, by again our limit comparison test. Okay, let's take a look at another one. Determine whether the series converges or diverges. All right, so the thing I'm looking at is basically this n plus 3 is problematic and this n plus 5 is also problematic. So I kind of want to simplify both of these things, just like we did in the previous one. That's my first go-to. This is going to be 2 times the square root of n over, well, I'll write it out, plus 3 over n plus 5. Okay, so this is our thing that we want to compare it to. And like I said, I'm just going to simplify it a little bit. This is 2 square roots n over n, something like that. Now we know, again, I'm just dropping these constants. And technically speaking, I could potentially just drop this constant too if I really needed to. But since the constant doesn't really make any effect on whether it converges or not, then I'm not too concerned about it. Okay, so that is to say this is 2 to the n to the 1/2 over n. So that means this we have 2 over n to the 1/2, something like that. Okay, now n to the 1/2, that diverges, okay, because this is again a power series and our power here is less than 1, so this diverges. Okay, so if this diverges, then maybe this also diverges, and we'll see that through our limit comparison test. I was spacing there on the name. Okay, so we will take the limit as n approaches infinity of our 2 square roots n plus 3 over n plus 5. And we're going to divide that by this thing here, 2 over the square root of n, which is the same thing there. Okay, so that means that we end up with 2 square roots n plus 3 over n plus 5 times the reciprocal, so that would be square root n over 2. Okay, and again, this is the limit as n approaches infinity of this thing. So our 2's cancel, and I can put this n into there, so that would be the square root of n squared plus 3n if I need, over n plus 5, and this is the limit as n approaches infinity. Okay, now if we take a look at this, what's the biggest power on top here? Well, it's this n squared, technically inside the square root of n squared. So basically it's square root n squared, which is square root n, or excuse me, which is just n, over, in this case, the only one that matters is n, the limit as n approaches infinity. Now, technically speaking, this is actually the square root of squared. That would actually be an absolute value, but since n is absolute anyway, it doesn't really matter. So we end up with n over n, which is 1. Again, another 1. Because again, these are basically the same functions, and so this ratio ends up basically being 1. And so that's what we end up with, and that's why we get a lot of these 1s, is because this ratio is often, if we choose our series correctly, we often end up with something that, while they look pretty different, I mean, they're definitely different looking, they are so close to each other that they are treated as basically the same at the infinites. Because at the infinites, I mean, think about it. This 3 is meaningless, and this plus 5, absolutely meaningless too. So because this thing here is 1, and this one diverges, then they both diverge by our limit comparison test. Okay, so in this one's a bit of a doozy. So we're going to determine whether this series converges. And factorials are always kind of annoying. Whenever I ran into them as a student, I was like, oh no. So factorials are kind of irritating, but also what's also irritating about this one is an n to the n, because n to the n, you know, if this was like n to some constant, like 5, that's a p-series, but it's not that. And if we had like some value to the n, that would be a geometric series, but it's not that either. So it's this kind of weird combination of both a p-series and a geometric series, which is not great for us. Now, whenever I see a factorial, there's a few things that's going through my head. First of all, what is n factorial? If we think about it, that would be like n times n minus 1 factorial, i.e., you know, n times n minus 1 times n minus 2 times etc., 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 until 2 times 1, right? So that's something to keep in mind. So when I want to like cancel part of n factorial, then what I would often do is maybe divide it by like an n minus 1 factorial or an n plus 1 factorial, because n plus 1 factorial will be n plus 1 times n factorial, and so the n factorials would cancel and be left with like an n plus 1. So that's something to be aware of, is if I really kind of want to get rid of it, I use like plus 1 or minus 1 factorial and kind of deal with it that way. But to be honest, it's not really the issue. I actually would like it to be gone, and I would like this to be mostly gone, because if this was completely gone in my like limit comparison, then this would just go to 0, because it'd be 1 over something like infinity, which would go to 0, and that would tell us nothing. So while I do want my n factorial gone, I also want most of this gone, but I want it to be gone in such a way that it grows basically the same, so it doesn't go to 0. So that is, the top I want to be growing basically the same as it, but like just a little bit different. So not exactly the same, but almost the same. And so I want this gone through that concept. So I'm going to choose some value here. So n factorial over n to the n, and I'm going to do a limit comparison with n factorial over n plus 1 to the n. Now, to be honest, we could probably do a direct comparison in a bit using the same logic I'm going to do to show that this converges, but I find that this one is potentially a little more obvious. So let's show that this thing converges first. So how do I know that this thing even converges in the first place? Well, basically, if we think about n factorial, again, that's n times n minus 1 times n minus 2 times ... 2 times 1. And this is all over n plus 1 times n plus 1 times n plus 1 ... times n plus 1. This is n times, so n plus 1, which is the same number of times as this factorial. So if we reorder this and instead start with the constants, we had like 1 over n plus 1, and I split them along these, each one individually, because I can do that with our times. It's the same thing. So it'd be like 1 over n plus 1 times 2 over n plus 1 times 3 over n plus 1 times ... until we get n minus 1 over n plus 1 times n over n plus 1. Okay? Now, no matter what my n is, okay, this thing right here would be the biggest fraction there, n over n plus 1. And this right here, n over n plus 1, is less than 1. Correct? So like this thing here is clearly less than 1. Just barely, but it's less than 1. And then this must also be less than 1, and this is significantly less than 1. So all of these things are some things to that are less than 1. And so basically we have some value that is less than 1. Okay, so this thing here is less than 1, and every one of these is less than 1, being raised to the n power. So we have some quantity less than 1 being raised to the n power. Now that right there is, by definition of a geometric series, a geometric series just requires that the r be less than 1. And our r here, or this thing, even though it's technically not constant, it's varying, it is some value that's varying that's less than 1. And it's greater than 0. So it's like between 0 and 1. It's somewhere in that range, and it is being raised to this power of n. So by geometric series concepts, this then has to converge. Because a geometric series that was, if we had a geometric series of 1 over n plus 1 to the n, then this would converge. Because again, this right here is less than 1, no matter what n here is. Okay? And all of these other ones, they would definitely converge as well. Again, because they're each smaller than that. Okay, so it converges. All right. Now, let's see whether or not, like, because if we think about this, n plus 1, this is now a bit, this is bigger on the bottom. So that would mean that this is smaller than this one. So we can't use like direct comparison between these two to show that they converge, but we'll do a limit comparison. So the limit as n approaches infinity of n factorial over n to the n over n factorial over n plus 1 to the n, we end up with n factorial over n to the n times n plus 1 to the n over n factorial. Okay, so those cancel, and we're left with the limit as n approaches infinity of n plus 1 to the n over n to the n. Now, if we think about this, n plus 1 to the n, n to the n, we could write this as big parentheses n plus 1 over n to the n, right? So these two things are the same because they're the same power. We can write it like this. Okay, now we can split this along the positive, the plus here, so we get like n plus 1 over n like that. We're splitting it, so this would be all to the n still. So this would be 1 plus 1 over n to the n, and the limit as n approaches infinity. Okay, now you might say, okay, well that would go to 0, and so 1 to the infinity would be 1. But that's not actually true. It's not that. Okay, what this is if you recall from my pre-calc class, if you've taken my pre-calc class, I actually do talk about this value right here. What is this value actually equal to? Well, let's think about it real fast. Let's look at it, I mean. So we have 1 plus 1 over x. Now, realistically speaking, even if you've taken my pre-calc class, you probably don't remember this. But I do mention it. All right, so let's look. There's some horizontal asymptote. Clearly there's a horizontal asymptote, right? This is very obviously a horizontal asymptote somewhere. And that somewhere is somewhere in the range of above 2.6-ish. Okay, now, what is that number? It's E. This is Euler's number right here. Okay, this is our horizontal asymptote, E. Now, this is actually the definition. Now, notice I'm only out to 130, okay? I'm not out very far. Let's zoom in here, okay? So we are still a little bit below it, okay? So let's zoom out a bit. Let's go at 1,000, okay? Which, again, isn't very far out. So at 1,000, if we zoom this in, okay, we're getting this value here. Again, it's still under that, but notice they're getting really, really close, okay? So the point here is that this is very clearly, you know, E. I mean, we can see that on this thing, okay? So the reason I recognize this as E is because that's actually the definition. If you recall from my my pre-calc class, this is actually how we define E. And kind of one of the when I talked about this, this is basically when I'm showing how we go from a equals p times 1 plus r over n to the nt to a equals p e to the rt, something like this, is basically, they essentially looked at like 1 plus 1 over n raised to the n, where we took n to infinity, the number of compounds to infinity, and we found that this ended up being e. And so that's when I mentioned it, just so you know, if you've taken my pre-calc. Again, it's not all that important necessarily to remember that e is defined this way, but e is defined this way. And if you don't remember that, I'm not surprised. Okay, so that's our little bit of clever aspect here. And so since this is e, it's not 0 and it's not infinity, it's a constant, well then both of these must do the same thing. So this converges, so this also must converge through limit comparison. So they both converge. Okay, so that's one way to show through limit comparison that this thing converges, but it's not actually the only way. And to be honest, if we use this logic, we could probably use the same logic in direct comparison. The problem is we can't use this thing as a direct comparison. But let's think about this as a direct comparison. So let's just think about what n factorial over n to the n actually is again. So this is n times n minus 1 times n minus 2 times dot 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 times 2 times 1. And this is over n times n times n times n times n times dot 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 times n times n. Okay, same number of times. Okay. Now, reordering this again, we have 1 times 2 times 3 times 4 times dot 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 times n minus 1 times n. Okay, and I'm going to split them along that, so it'd be n, 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 n. Okay, now let's think about what these values are. What's n over n? Well, n over n is like 1. Okay, now n minus 1 over n, that would be like something less than 1. So if I just called this one 1, and then the 1, and 1, and 1, and 1, all of these are less than 1. And so this 4 over n would also be less than 1. So I'll call it a 1, and a 1, and a 1, until we get down to these last ones, 1 over n times 2 over n. So basically, if we compare this to this statement where I'm just calling each of these 1 because this is 1 and then this is less than 1 and so is this and so is this, then that tells me that my sequence n factorial over n to the n here is less than or equal to 1 over n times 2 over n times 3 over n times 4 over n, as many times as I really want to do it, but this will be sufficient because I'm just trying to write a convergent series. So times 1 times 1 times 1 times 1, okay, which is just 1 over n times 2 over n, which is n factorial over n to the n is less than or equal to 2 over n to the 2. And if you recognize this, n to the 2, that's a p-series, and the reason I did it to the second one here is because it's a p-series where our power is greater than 1, and that's all I really needed to show, that this right here then converges. And since this converges, then this must, because it's less than it. Now, the reason I stopped here and not like, say, 1 over n times 1, 1, 1 is that this diverges, and being less than a divergent series doesn't tell us anything. So we wanted to go further. And why didn't I go even further? So, 1 over n times 2 over n times 3 over n. Well, because I didn't need to, because 6 over n to the third power is also a convergent p-series. I could also have used it, but this was all I really needed to do to show it was convergent. So this is a direct comparison convergence test here. And so by direct comparison to this thing here, it converges. And really, if I'm using the logic that I did to show that this one converged, it's not a huge stretch to just find this convergent series as well. But as the concepts are very similar, but they're a little bit different. So either one would work to show that this thing converges. So like I said, a direct comparison would have worked right here, but also a limit comparison would work, just depending on which one we ran into. But those are just two ways that we can solve this. We'll eventually get other methods that could also solve this that require a little less critical thinking, which is always a plus, right? You know, I don't want to have to think on these problems. I want to just be able to plug it into the method. But a lot of times when we run into oddities like this, again, problematic things being it's not p-series or geometric and a factorial, that's also annoying. We have to get a little bit creative. Anyway, so that then is our comparison tests. That is direct comparison and our limit comparison test. Thanks for watching.